Welcome in the video describing how validated process data can help in better monitoring and optimization of industrial processes. Attention will be also paid to further activities like plant performance analysis, equipment functioning diagnostics, and how to support plant operators in optimal controlling of production. Our software for plant mass and heat balancing, data reconciliation and validation Recon is used in process industries for many years. We hope that this presentation will show further possibilities of using Recon for optimum control of production and also for economizing consumption of raw materials and energy. In other words, how to recast the better information about your plants into money. Let me to give you a brief info about us. Chemplant Technology was founded in 1991 by chemical and power engineering professionals. The major activities at present are software and engineering services for process industries, mostly chemical and petrochemical plants, refineries and power plants. Plant performance analysis and optimization and decision support systems. Chemplant is the global leader in process data reconciliation and validation methods. For example, the book Process Plant Performance is the first book devoted fully to the problem of systematic monitoring and analysis of plants in process industries. The book Material and Energy Balancing in the Process Industries is the comprehensive description of balancing methods, from microscopic balances to balancing of large plants. Important features of both books are process data reconciliation and validation. Chemplant developed software pro process industries for more than 30 years. Chemplant's flagship is Recon, the software for mass, energy and momentum balancing and thermodynamic modeling with data reconciliation and validation. Recon is accompanied by the bundle of supporting software, namely, gathering data from industrial data sources, equipment performance analysis and diagnostics, data storing, visualization and reporting, which is managed by the Process Data Information System (PDIS). Important are software modules for simulation based on actual process data, including what-if queries. The Data Miner module, which is the linear or nonlinear multivariable correlation and regression analysis system. By several keystrokes you can discover relations between process variables and key performance indicators. The Energy Management System, EMAN, serving for monitoring and analysis of using utilities like steam, fuels, etc. From the energy consumption point of view, data gathered by Recon can be easily analyzed by the well-known pinch method. All this is the complete solution which needs no third-party software. Recon's primary task is to guarantee data reconciliation and validation, which is based on rigorous models like mass and energy balancing or thermodynamic calculations. The most important targets are obtaining more precise measured data, finding best values of calculated unmeasured variables and model parameters, elimination of possible gross errors in measured data or in models, to have the complete information about uncertainty of results, to help in instrumentation maintenance and improvement, to transfer process data into information which helps operators to maintain production in optimal state. In words, we need to transfer raw process data into good validated data. It is needed to avoid so-called garbage in, garbage out effect. Basic steps in performance analysis, equipment diagnostics and optimization are building up mathematical models, setting up complete reconciled and validated mass, component and energy balance, saving validated process data to a long-term database for detailed statistical analysis for later data mining, implement process data-driven simulation and what-if queries, prepare equipment degradation diagnostics, enable decision support for offline optimization by operators via performance analysis dashboards. Models in Recon can be of different size, from simple models of individual unit operations to models of overall plants with hundreds of nodes and streams. Recon can manage in one installation several different models simultaneously. Greater part of modeling is done via the graphical user interface. There is also possibility to add user-defined equations. The editor of user-defined equations contains the configuration screen with many thermodynamic functions and access to the Recon's physical properties databank. The equations editor enables also logical conditional programming. The third possibility of modeling is the use of empirical or regression models. The existence of historical database makes possible to create easily empirical models which can be used for enhancing theoretical models. Building of empirical models is facilitated by the data mining module which integrates Recon with the historical database. The example on this screen shows so-called quality estimators, which are regression models predicting composition of products from online measured variables like temperatures, flow rates or pressures. It is well known that the chemical industry is based on chemical reactions. Recon makes possible to model reaction by two ways. The first possibility are classical chemical reactions which are stored in Recon's reaction databank. The other possibility is the balance based on chemical elements, which means elemental composition of individual components. The composition is taken from the Recon's database of chemical components. This way can be used in biotechnology, pharmacy and similar areas with complex chemical reactions. Chemical plants are frequently accompanied by their own energy cogeneration system which provides steam and electricity needed for production. Recon is very rich in methods for modeling systems where energy savings are important. Models range from a simple heat recuperation to complex systems with boilers, turbines, etc. Here are two examples. The first is the vacuum distillation of heavy crude oil with 24 heat exchangers which provide the heat exchange between hydrocarbons. Some of them also serve for steam generation and products cooling by water. The second example is a coal-fired steam generator with air preheat. The existence of a model makes possible to calculate parametric sensitivities of important KPIs on model input variables. Parametric sensitivities are the standards outputs available in Recon. For example, how will be changed the specific energy consumption if the heat transfer area will be increased by 10%. Parametric sensitivities are useful for optimization studies. In Recon is possible to have for one base model also one or more model variants. This feature is useful for so-called data-driven simulation. This is done in two steps. In the first step, the base case model serves for data reconciliation and validation. Results of this step are reconciled measured values and also model parameters like heat transfer coefficients, equipment efficiencies, etc. In the second step, the simulation variant of the model uses values of parameters as inputs and some previous input variables are calculated from the model. In other words, the DVR model and the simulation variant differs mainly what are inputs and outputs. Such solution is useful for example in what-if studies which will be shown later. Important is also the data management. Historical data obtained during drive are invaluable for plants' performance analysis and optimization. There are at least three possibilities of saving this information. The most simple is the Microsoft's Access database. Recon has its built-in access capabilities so that you need not have access installed in your PC. This is very simple solution in Recon. You can create it by several keystrokes on your PC. The more professional solution is the Microsoft SQL Server database. In its Express version it is still free on your PC. But its setting up is not so simple as MS Access. The advantage is that with it you can use all functions of PDIS. The third possibility is to integrate Recon with your corporate historian of process database like PI, PhD or Info Plus 21. This possibility can be combined with both previous options. Performance analysis is usually based on comparison of the actual plant operation with some reference state. The reference state can be, for example, the design state or some well-defined state with ideal production conditions or ideal process control. Performance analysis should be able to identify losses or gains caused by differences between the actual state and the reference state. Performance of a plant is usually characterized by important plant's KPIs like yields, heat rates, etc., which can be expressed also in money units. The main idea of the performance analysis is that it has no sense to compare actual plant state with the reference state directly. There must be done correction for any difference between variables in actual and reference states. Here is one example. The main KPI of a steam cycle is its efficiency expressed as the heat rate. Heat rate depends on the temperature of cooling water. Colder water means higher efficiency and vice versa. The actual heat rate must be therefore corrected for the difference in cooling water temperatures. In the figure right on the axis of cooling water temperature is the temperature Rs for the reference state and the temperature Os for the operational state. The heat rate for the operational state belonging to the circle number 4 must be corrected for the temperature to the reference state shown by circle 3. In this way, the overall gross heat rate difference between points 4 and 1 is corrected. The heat rate change belonging to the equipment degradation is given by the difference between points 3 and 1. All this holds for this simple example when the cooling water temperature was the only variable influencing heat rate. Similarly, this must be done also for differences of other significant process variables. Factors that influence the overall plant economy belong to 3 categories. In the first category are external factors like the raw material quality, ambient conditions, plant load. These factors can't be influenced by operators. In the second category are internal factors which can be influenced by operators. This is the problem of the proper plant control. In the third category are losses caused by the equipment degradation. This can be influenced by operators only partially. In some cases, for example, by cleaning of heat transfer areas. Some equipment degradation can require deeper maintenance. A good performance analysis system should be able to separate the influence of 3 categories above and to quantify the amount of money which are lost by them. While the influence of external and of control variables can be calculated from the model, the overall influence of equipment degradation is difficult to quantify directly. We recommend to use the overall balance of differences. Here we suppose that the total gross difference is the sum of remaining 3 differences. In the next slide, there is the example, the performance dashboard for a coal-fired supercritical power plant. The main KPI is the heat rate defined as the amount of input energy, coal, needed for generation of unit amount of electric power. The dashboard is divided into 4 horizontal fields. In the first field is shown the gross difference between the actual state and the reference state. You can see also the difference in steam cycle efficiency and the difference in the boiler efficiency. In individual columns can be seen differences in numbers and also the graphical presentation in physical and money units. By clicking on every object, an operator can see the trend of selected variable in time. In the second field are differences caused by external variables which operators can't influence. In the third field are differences caused by individual controllable variables which can be influenced by operators. This field is the most important information for operators. They can see here which process variables are not controlled properly and what is their impact on the plant's economy. In the last field are differences caused by equipment degradation. It should be noted here that this value may contain also the influence of some neglected variables. The following part of the presentation concerns energy consumption management. The suitable method for energy consumption analysis is the online analytical processing, abbreviated as OLAP. There are 3 main dimensions of the problem which can be depicted by the so-called OLAP cube. The first dimension is the structure of the company, namely its plants. On the second level, every plant can have several producing units. The second dimension is the set of utilities which provides different kinds of energy. The third dimension is of course the time. We need to analyze historical data, compare different production regimes, etc. The solution will be illustrated on the next screen. This screen is the example of online monitoring the energy consumption by the energy management system EMAN. Let's suppose that a refinery consists of 3 plants numbered 1, 2 and 3. In refinery are used 3 kinds of utilities, namely 2 kinds of steam with pressure 0.65 megapascals, pressure 1.6 megapascals and the fuel oil. Individual plants can have several producing units. The individual utilities have their price, and also it is possible to sum their overall energy consumption according to their content of useful energy, so-called exergy. There are 2 prerequisites of this solution. The first is that all utility streams are measured or otherwise known. In practice, some utility streams are not measured and can be only calculated or estimated. Important is that the balance should be reconciled. This means that all inputs are allocated to consumers or to losses. All this can be implemented via recon. The second prerequisite is that there exists a model for calculating standard target consumption of utilities for a given production. These values are usually available from the design or from other corporate documents. The ratio of the real utilities consumption and the standard target in percents is called the relative energy demand, abbreviated as RED. With the knowledge of utilities prices, we can similarly define so-called relative money demand, abbreviated as RMD. It is clear that the nominal values of RED and RMD are 100. In the left upper corner is the device showing RED for the whole refinery. In remaining objects, their size shows their relative impact on the overall energy consumption. The color, from blue to red, shows increasing value of RED or RMD. The green color means the neutral value around 100. In the right upper part of the screen are bar graphs about using individual utilities. The first graph is in physical units, the second is in money units. The height of a bar and its color shows the relative energy and money demand. The width of a bar shows its impact on the overall energy consumption. Circles in the middle row of the screen show details about individual plants and their producing units. Areas of wheels show plants' relative impact on the overall energy consumption. The sectors of wheels represent the individual production units. Sector sizes show their relative impact in a plant. Colors represent the relative energy demand. In the bottom row are devices showing the relative energy demand for individual plants. Clicking on individual objects, operators can see trends or multi-trends of historical values. For example, the relative energy demand for the whole refinery, or detailed trends for producing units of a plant. A typical what-if query can be, what will happen if some temperature value will be changed from T1 to T2? What will happen if we have changed a raw material of quality A to quality B? Such queries can be answered by data-driven simulation described earlier. Recall the 2-steps approach. In the first, identify model parameters from actual plant data. In the second, simulate the plant with changed inputs. For example, change T1 to T2. Using what-if queries is simple. In the left panel, change the value in the column new val. After pressing button Simulate, program first imports real plant data and calculate model parameters. Then make simulation with changed input variables. Results can be then seen in the right panel. Detailed equipment diagnostics is specific for every kind of equipment. For example, there exists a large set of performance test codes for equipment like pumps, boilers, condensers, etc., by United States ASME, or similarly, there are performance test codes for European Union. Test codes require detailed calculation of parameters of equipment, which are model parameters, in the language of recon. Calculation reliability of performance test codes by recon is thus increased by high quality of validated data. The real parameters can be compared with values obtained from reference or design data and can be shown in dashboards. This slide is the example of equipment diagnostics. This is one of screens analyzing the group of low-pressure heaters of a supercritical coal-fired power plant. The analysis is based on ASME Performance Test Code 12.1. The yellow color of individual cells means that the function of a heater is in prescribed tolerances. The other colors, which are configurable, mean some significant difference between the standard state and the reality. All cells are clickable and they can show the history of this difference. This info can be accompanied by the written info for operators about possible causes of a problem. This slide has no ambition to address advanced optimization methods like real-time optimization or optimization by a plant retrofit. For the offline optimization of a running plant, we need to know: the first, what is the real state of the system? This means complete and reliable mass and energy balances. The second, to know the influence of control variables on the optimized KPIs. This can be solved by data-driven simulation or by parametric sensitivities. The third, how far are individual control variables from the optimum and what is their significance? This should be available for operators on the performance dashboard. Recon is not only a program for mass and energy balancing. Its process data analysis is enhanced by the possibility of the simulation based on real plant data. Recon's capabilities can be enlarged by its supporting modules: PDIS for data management and visualization, PDIS Rep for online reporting, EMAN for energy consumption monitoring and analysis, Data Miner for analysis of historical data, what-if queries. All modules are available free with the Recon Professional Site license. Hope that you have found this video interesting. Thank you for your attention.